now a second-year graduate student at Stewart Observatory at the U of A, and he's already discovered quite a few cool things, including this planet that is around 3 stars, and so he'll be telling you about that today. Thank you.
Hey guys. Thank you. Alright, I'm really excited to talk to you guys about this. I've given this talk before in various scientific settings, but this is the first time to the public. Can you hear me? There you go. Can you hear me? Okay. Great. If you can't hear me, yell at me, please. Higher. Here. Here? Okay. Alright. So I've given this talk in various scientific settings before, but this is the first time to the public, so if you're ever lost, if you ever have questions, please just speak up. I love giving conversational talks, not just one-direction talks. So, let's start. You've seen a lot of exoplanet discoveries recently. There are thousands, about 5,000 if we include our candidates that we're still confirming. What you're looking at in the movie is a top-down schematic view of the stars and planets in many of these systems that we found. And the solar system is on the right. You see Venus, Mercury, or wrong order, Mercury, Venus, Earth, Mars. Jupiter is, if I can find the laser pointer, this line here. So all of these solar systems, planetary systems, the point that I need to get across to you with this is that we only know of planets, for the most part, that are very, very close to their stars. And that's primarily due to just a simple selection effect, because this is how we're finding most of them, is by the transit method. You've probably heard of it. It's a really simple concept. You just look at the star, you measure its brightness. When the planet's in front of it, the brightness dips, and you see this periodically, and you know that it's a planet, but you don't really get very much information on the planet itself. What we really want to do is we want to be able to use just our conventional astronomy tools, just taking pictures with telescopes of the planet itself to be able to learn more about it. Here are half of the planets that we have directly imaged. There are about 10 of them. Half of them are in this system. There are only 10 out of these thousands of planets that we found that we have pictures of, because this is really, really hard to do. You can imagine stars are bright, planets are very faint. Planets are close to stars, so they're lost in the dazzle of starlight. If you look at these, you notice we blocked out the starlight. That's part of how we overcome the technical challenge. And that technology is called a coronagraph. This is actually a coronagraph on the sun, one of the first ones that was developed. How it got its name, to see the corona of the sun, this gas that's constantly outflowing. This is Comet Ison going around. This was actually supposed to be a really cool astronomical event. It's supposed to be one of the most spectacular comets, but it went around the sun and it just kind of got destroyed. But I like this demonstration of how a coronagraph works. And here we're doing the same thing, but now around another star, so that we can block out all of its light, most of its light, and see the faint planet. But that's not enough. The atmosphere is screwing us over also. So Decker mentioned adaptive optics. Basically what this is a deformable mirror technology. We have thousands of actuators acting thousands of times per second to move the shape of our mirror to kind of imprint the negative signal of how the atmosphere distorts the light, and put all of the light back to where it originally is before the atmosphere tries to screw us over. And we can make our images incredibly sharp. You put all of the starlight back on the star, not on top of the planet. We can see faint things next to bright stars. All of this data here is taken with the LBT up on Mount Graham. These are actually 2 stars, but how we do it is to look for planets, and even with those 2 technologies, it's not enough. We have defects in our mirror. The adaptive optics don't work perfectly. So what we get is all these stupid little speckles that are exactly as bright as our planet and just confuse us. The planet is in here somewhere rotating. I tried to find it before just by eye, and I can't. But what I use this video to describe for you is how we process this data once we get it to a computer. So, stars as they rise in the sky rotate with the field. The telescope just stays constant, sees the same thing. All of this light that the telescope's scattering just goes into this stable frame, while the field, the stars, all rotate. So we can use this to pick apart the noise from what's actually in the sky, subtract it off, and then we can find the planet in it. That's the third piece of technology that we can use to actually take images of planets around other stars. And I go through that because I think it's all really cool, and it's all really new. Not even all astronomers know that we can take images of planets around other stars, and have taken images of planets around other stars. And I actually think it's the way of the future. So like I said, we get a lot more information on the planets when we see their actual light. Right now we're only looking at giant planets, basically just because that's the easiest target. We're developing these technologies first. So we're learning all sorts of things about them, about their atmospheres, about their orbits. But really what the holy grail of this is pushing towards a future technology, a space-based telescope that can actually take pictures of Earth-like planets and can pick apart the gases and chemicals in the atmospheres of these Earth-like planets for signs of life. So in about 20 or 30 years, we're probably going to have another large space telescope, the successor to Hubble, the successor to James Webb, that's going to actually start the first scientific search for alien life. And we're going to do a little better than this guy, I hope. So for right now, like I said, we're developing this and learning all sorts of things about giant planets and pushing it forward for what the future may hold. So right now, what I'm working on and what others in my research group are working on is what we call the Scorpion Planet Survey. So we're looking at nearby young stars in the constellation of Scorpio. They're actually relatively bright stars. You can go out and see many of the stars we're looking for planets around just with your naked eye. And we're doing this not with the LDT, not with any telescopes in Tucson, unfortunately, because these stars are too far south. We have to go to Chile. So we're using the very large telescope. It looks very little up here on this mountain with the Pacific in the background. But it's actually 4 telescopes, 4 huge telescopes. The primary mirror of each of these about as wide from the bathrooms as to that wall over there. And our adaptive optics, camera, spectrograph, all of our instrumentation is inside of this big grand piano-sized thing that's constantly mounted to the side of this giant telescope. And let's get this out of the way. I'm not actually going to use it in the future, so don't feel like you need to remember it, but it's the most horrendous acronym I have ever encountered, and you need to share my pain. It's the Very Large Telescope Spectropolarimetric High Contrast Exoplanet Research Instrument. We have bad ones, but that's my favorite. So here are our stars. This is an actual picture that I just took with my digital camera of many of the stars in Scorpio and Lupus and Centaurus. You look in the southern sky in the summer, you can see these. The one that we're about to talk about that the planet is around is this one, this telephone number of a star. This faint guy right here. A little bit too faint to see with your naked eye, but go out with binoculars and you can actually really see it. And it's actually 3 stars. Not just 1, not just 2. In 1897, somebody looked at it with a telescope and saw that it was 2 for the first time, which probably just looked like this with the technology at the time. But now looking at it with this 8-meter colossal telescope, we can separate this star from these 2 stars. And this distance here is about 300 times the Earth-Sun distance, or about 60 times the Sun-Jupiter distance. And to put it all into the context of the solar system, planet included, here it is. Here's our estimate for the planet's orbit, the orbit of the stars. Since we've actually observed the stars for 100 years, we know what their orbit is. We know that they're actually this close to the planet. The planet we've only seen for a year, so we can only make guesses at its orbit right now. And it's kind of surprising when you put it into context that there's something that, I told you it's a giant planet, but I didn't tell you its mass. It's about 4 times as massive as Jupiter. And it's outside of even Pluto's orbit in our own solar system. Pluto is about 1,000,000 times less massive than this thing. But this star is only twice as massive as the sun. So it's kind of a mystery how 4 times the mass of the solar system ended up outside of where all of ours is contained. And even more so if you consider that there's 350% of the stellar mass of our solar system. So I told you that we'd only discovered this planet last year, and that we can only make guesses at its orbit. That actually is what I think is the most interesting and the most exciting and the most unique thing about this, and what this system teaches us the most about in terms of what other types of planetary systems are out there, So for right now, there are two possibilities. It's so close to the other stars in the system that we don't know if its orbit is stable. We ran simulations, and they show that it can be stable for as long as the system is old, or we might be catching it at a very special time where something else is going to happen. What do you think is going to happen to this planet?
Shooting off.
It kind of gives it away. So also, like Decker showed that simulation of the three-body problem, it's the exact same thing, except here we have a four-body problem. So these stars we know are about 17 million years old, and I'll ruin how the movie ends. The planet ejects in 10,000 years. So because of that, we think we're probably not catching it at a very special time. We're probably looking at it more in this stable situation where this planet is going to survive and just continue to orbit with 3 suns. But we can't really rule this one out yet. But we'll be able to tell you more about that maybe in about a year when we get our next observations. We can see exactly just where this planet is headed.
So how much does your variables have to change for? I mean, how is it like right?
No,
on
it's
the
extremely chaotic.
Well, is it right on the razor's edge of being stable or unstable right now?
Within there are many stable orbits and many unstable orbits. We can't really do a sort of, there are more space for it to be stable. It's pretty much equivalent. So it didn't come back, it's just looping, it's gone forever. So how did it get there? It's kind of a mystery, and we kind of want to figure it out because it can teach us a lot about how planets form and about what other types of planetary systems might be out there that we didn't imagine and maybe even didn't even look for because we didn't think that they could exist. So maybe it just formed there. Well, that seems pretty unlikely. We think that planets form in disks of gas and dust around the stars that function the same way as planets do under gravity, and there just wouldn't be enough mass left over here in this unstable region for this planet to form. These stars would truncate the disk right at about where this planet is now. Maybe it formed closer to this star and just got kicked out. Maybe there's another planet in there. We can test that by going and looking closer, seeing if there's another planet. Maybe it formed around these stars. That actually seems like it could be rather likely with what we just saw many examples of the three-body problem. Or maybe it formed in a totally normal spot and the stars just evolved. Their orbits changed subsequent in their lives and made it look like it's in a weird spot now, when really it was made in a totally normal place. So I think I'm way under time, but I was planning on getting more questions. So I'll leave you with this movie, which is my favorite, and I'll take questions.
Given all of the current technology, how far away would we be able to see our own solar system or something similar to, and detect any of the planets?
Which planets? So,
like even Jupiter.
So the question is, how far away could we be from our own sun to detect Jupiter? So Jupiter is at 5 AU. We can detect things around these stars that are 300 light years away at about 10 AU. So at about 150 light years, maybe out to about 200 light years from the sun, we could see Jupiter with our current technology. Now we're at a pretty narrow moment in our history where we've evolved all of this technology very rapidly. So I think that if there are civilizations out there that are looking to image planets, that another 20 years they could image Earth, not just Jupiter. Just like in another 20 years we're going to be able to image Earth-like planets around these stars, not just giants. So I don't know, that's a big thought question. Yeah, nice.
Do you think planets around binary stars or triple stars are more common than around single stars?
They are just as common around multiple stars as they are around single stars. These ones that are really far out, we don't really know that yet because we haven't really explored it. But at least what we're finding from the planets that are close to their stars is that there are just as many planets that are in multiple star systems as there are in single star systems. Just like there are just as many multiple stars as there are single stars. binarity is a huge thing in the stellar formation process. Yeah?
If the planet is in a stable orbit, would that orbit be similar to the theoretical planet X in our solar system, which is also very large, really far out?
So by planet X, you mean planet 9?
Yeah.
So if planet 9 exists, it's definitely the most similar thing in our solar system to this, just in terms of mass and where it is in its orbit. I think that's posited to be around a Neptune mass, though. This is 4 times as massive as Jupiter, so it's still maybe apples to oranges. Yeah?
How do the size of the 2 outer stars compare to that of our sun?
So the most massive star is the lonely star in the system. It's 80% more massive than the sun. The next one is almost exactly as massive as our sun, 0.96. And then the other one is 60% as massive as our sun.
So then how much of an impact if the 2 outer suns are that much smaller and that much further away from that particular planet? How much of an impact do they really have on the orbit?
So as you saw from the unstable one, if we move the planet just a little bit closer, a lot, or if we make the planet's orbit a little bit eccentric, where it can move further away, it's not always at the same distance from the star, it can impact it a lot. They are far away. It's 320 times the Earth-Sun distance between the stars, but the planet's at 80 times the Earth-Sun distance from the one star, and it's roughly equal mass between star A and star B plus C. So the forces do still add up to be significant. All right, no one else? All right, well, thank you for your attention.
Thank you for coming to this month's edition of Space Drafts. Our next one will be October 19th, and we'll also have one at the end of October as well, and then we're going to take a break in November. So stay tuned online for the schedule, but the 19th is the next one. So see you then. Thanks.